design whatever we are going with. Okay, and later in which you can also do this kind of design with your own measurements. Yeah, now I want to calculate for 443.7 megahertz, right? So it's 3 into 10 to the power of 8. So what I'll directly do is, so 3 into 10 to the power of 8, already I've done it. So divided by yeah. So 3 into 10 to the power of 8 divided by 443.7 megahertz, right? So 443.7 443.7 into 443.7. So the desired frequency is 443.7 megahertz. So you have to divide your C value. C value in the sense it's nothing but 3 into 10 to the power of 8. So that's the reason I've took this. Then divide by 443.7 into 6 10 power. So here I'm getting 0.6761325 meters. So if I convert this into in terms of millimeters, so I'm getting lambda value, I'm getting somewhere like 676.1325. So if I divide this by 2, approximately it would be 338.06625 or 337.8. Approximately the same length has been taken. So in this way, we have to actually consider this particular length of the half wavelength dipole. So this is how we'll be actually calculating. So for whatever antennas you are going with, wherever there is a dependency on lambda, you have to go ahead with this kind of procedure. So the accuracy, why exactly we have to 337.8 is basically when you're going for this kind of designs, if you're going for a theoretical formula, there would be a small deviation in the performance. So if you are taking a slight less when compared to the actual calculated formula, you will be getting a perfect performance at that particular frequency. Okay, so here if you see, we have set it up to 337.8 mm. So this is my length. So I can completely operate this particular antenna now. And the complete radius, what you can see, it is for 1 mm. So note down these kind of parameters, whatever we have, and then get started with the things. So as of now, I'm opening the software. So in order to get started with the dipole antenna, so we can directly get started with this particular node option. You can go to node. There is an option, node. Click on by XYZ locate. Okay, so first point, I just want to locate exactly at the origin, that is 0, 0, 0. Just click on apply. And then now it is asking for the second point. Second point should be exactly half of your lambda by 2. that is lambda by 4. Why it is called as lambda by half wavelength dipole is the complete length. Sir?
Is it other students, they are able to see the numbers? Just can you ask?
1 second, sir. Guys, are you able to see the numbers, whatever we can see here, or else should I go for magnification? If you advise me to go for magnification, I can go ahead.
Yes, sir, if you could magnify it.
Yeah, fine, great. I'll do that. So initially we just went with node. Once we have clicked node, we have got by XYZ locate. There is an option where we can create multiple nodes. So here we are actually preparing a dipole antenna with nodes itself. It doesn't require any additional computations. So if you we have noted down that the half wavelength dipole length is 337.8 mm. So I want to create exactly 3 points for this particular antenna, because I have to give the excitation exactly at the middle position, exactly at the center of your particular wire. You have to give your excitation. So now let us just get started with this particular thing. So, and even in the design document, what we have referred in the design document, it is mentioned that we have to elongate this particular antenna in the Z axis. So X and Y, I'm leaving it as it is. Just I'm trying to change my Z value. So Z value should be exactly half of the length what has been specified in the design file. So in the design file, it is mentioned as 337.8 mm. So you have to divide with exactly 2. So let us just calculate it. 337.8 divided by 2. It's 168.9. So let us just put the same parameter, 168.9. Just click on apply. So there will be one more node will be created. One more node will be created at the second position. And similarly, the third node should be created exactly at the same height of your dipole. That is 337.8. Okay, 337.8. Now we are done with it, done with the complete design part. I mean, the nodes part we are done with. Now we have to connect the nodes also. So if you click on F, you can actually, 1 second, I'll show you. So basically you'll be getting a design in this particular format. If you just click on F, what happens is the complete design will be fit into a single region. Okay, that's possible. So this is the first step what you have to do. Here we have created 3 nodes, all the 3 nodes. You can see one node is at the bottom, the middle node is at the top, and the top node is at this particular position. So we have to combine all these nodes together and we have to excite at this particular point. That's the reason I have took exactly half. And the name why exactly dipole is called half wavelength dipole, it's called about is the complete length of dipole is equal to lambda by 2. That's the reason it's called as that particular thing. So now what we can do is we have to go for node. Again, we have to select the node option. Then we have to go for on curve. So we'll be getting a 1 second. So here, just go to node. Under node, we have on curve. Select on curve. So you'll be getting a menu here. Okay. Select your nodes one after the other. 1 second. Okay. So you have to go for 1D, go to on curve, select this on curve. So here now you'll be getting in terms of curve. Earlier that is also on curve only, but that is related to surface edges. So we have to go for this particular on curve. Now we have to select the elements here. One second, there's some issue. So here, first thing I have to join up my nodes. Whatever nodes I have to join up them. So let us go for curve. Let us go for sketch. Let us go for pick points. Whatever points you have, just go and click on them. So your method should be smooth, and even your projection should be 3D. Even though it is 3D, it's fine. Just click on apply. So once I click on apply, I can see there is a single line has been created for this particular region. So I've connected all the dots together. So this is exactly my middle point where exactly I have to excite, and this is my top point. So once you're done with this, we have to go for 1D. On 1D, we have on curve, select on curve. And here you have to select the curve. Select this particular curve, whatever we have covered so far, and let the number of elements be 10. Once you have entered 10 here, click on generate 1D. So here 1D elements will be created on the structure. So we'll be getting multiple slots. So exactly in the middle, there will be one slot will be available. So this is done. So once you're done with that, click on close. So here you can see parts. This is a part information. If you click on part, the part will be excited. You can see the part. Similarly, these are the nodes. I hope this is not saved. 1 second. Curve. Selected. Generate 1D. Apply. Yeah, now we have got the elements. Now we have got the elements. So earlier there was some issue. Fine. So first step, what we did in the mesh is first we have came up with node. We came up with by XYZ locate node. So we have created some nodes, 3 different nodes we have created. One is at the bottom, other one is at the middle, and the other one is at the top. After that, we came across the curve. We have sketched a curve between your all the points, whatever you have created, all the nodes. Once that is done, we have came across with this 1D. We have selected on curve. In on curve option, I have selected my curve. I have given number of elements as 10, and I've given my generate 1D. So this is done. So this is done. So here nodes are also given, the elements also you can see. So we have elements in each and every point. At 10 mm of gap, you will be actually having the elements because I've completely divided the parts into 10 parts. So once this is done, you're done with this particular meshing part. Now you can actually go to the SEM part. Since this is a dipole antenna, it's not that critical to go ahead with. So now we have to switch up to the SEM part. So here the analysis, whatever analysis checks, whatever you want to do, it's not required because it's a very thin line what we have created for. Whatever dipole antenna we have created, it's a thin line antenna. So there is no need of going with any sort of checks. So let us just go to SEM. So now we have come to SEM window. So whenever you have come for SEM window, the first operation what we have to do is we have to go to view menu. Under view menu, you have to go to the bottom, and the bottom side you have something called as SEM tree views. So this is nothing but SEM tree views is nothing but you are assigning what kind of methodology you want to go ahead with. Either you want to go with PAM-SEM, either you want to go with PAM-SEM FDTD. If you're going with time domain, you have to go ahead with this. Similarly, if you're going with high frequency, you have to select this. Similarly, if you are going with modeling, cable modeling analysis and cable analysis, you have to go with crypt. If you are going with E-field FD, you can go ahead with this, the frequency domain, whatever we are solving now. If you want to go for E-field time domain, you can go ahead with that. And even SEM time domain also, you can go ahead. So you have to select the parameter. You have to select the parameter E-field FD. So once this is done, once this parameter is done, and there are some measurements also you can do. You can select your measurement. You can select the measurement between 2 points. You can select it. Okay. There is some editing I need to do it because the initial units what we have took is for mm, but here we have got it for meters. So let us just go ahead back once again. Delete this. So once again I'll repeat it. Whatever nodes also we have, let me delete this. So let me go back to mesh. So in mesh, the first step, it's a better practice for you. What you have to do is you have to go to tools. Under tools, you have to select change convert length units. Select this as mm. So whatever units you have in your design, select that particular unit first. I'll show you once again. Go for magnifier. So under mesh, under tools, you can see we have change and convert length unit. Once if I click on that, I'll be getting a length unit. Under length, you have to set up the length and click on OK. So now it sets up to the mm range. So once it is done, once this is done, we can go ahead with the same procedure. So go to node, select by XYZ locate. First node should be created 0, 0, 0. Second node should be created 0, 0, 169.8. Sorry, 168.9. And the third one should be created exactly at 337.8. Apply, close. So once you're done with this, if you click on F, the complete antenna will be, the complete node points will be available within the structure. So once we are done with this, we have to combine all those curves. So in order to combine, you can go with curve. You can select sketch. Curve, sketch, select this particular point, all the points. So in a linear manner, you can select it, click on apply. So we'll be getting a part. This part you can directly name it as your dipole. You can change the name of the part. So in order to update the part names, directly press F11. You'll be getting a part manager window. Open it. Name it as dipole antenna. Don't give any spaces behind. Done. So we have got this close. Now what I need to do is I have to go for assigning of number of elements, sub elements onto the same part. So you can go for on curve 1D. You have to go for 1D. On curve, on the curve you have to do the optimization. Number of elements would be 10. If you want to go in terms of element length also, it's fine. Element length, if you want to go ahead, you have to go for 337, 33.78 should be your element length. If you want to go for number of elements also, it's fine. So select curve, click on curve, click on your original curve, whatever you have selected so far, click on generate 1D. So 10 parts will be generated. Click on apply. So once you click on apply, the parts will be applied up. So at the left side also, you'll be getting number of elements. So once we are done with this particular part, we are done with the meshing window. We have to switch down to the SEM window. So go to applications, click on SEM, click on SEM. Once it is done, now we have to go for view. Under view, we have SEM tree views. Under SEM tree views, we have E-field FD. So this is done. It's already configured to E-field FD. There is no need of any change. If you are for suppose if you are choosing any other methodology in a different project, next time you have to change it. By default, whatever you're choosing in the previous stage, that will be preserved. So this is okay. This is fine. Now, if I go for SEM,
Sir, sorry for interruption, sir.
Yes, sir.
Sir, what is the use of elements in the antenna?
Which one, sir?
Elements.
Yeah, I'll tell you, sir.
Yeah.
See, elements, whatever we have created in this particular antenna structure, it actually divides the complete problem into subparts, sir. So whatever I've told you the concept earlier also, like mesh or else the subparts what we'll be creating from the original antenna, this is also the same procedure. So we are actually dividing the complete antenna, which is of 337.8 mm into 10 subparts, wherein with we'll be actually calculating the performance of each and every small part. So we are dividing the complete problem into subparts and trying to solve it as early as possible with a parallel computation. That's the reason we'll be actually using these elements.
Okay. Okay.
Yes, sir. So coming to SEM window, now SEM is the main window. Under SEM window, visual SEM window, you'll be having a SEM option. Here we have to configure all the parameters. So first one, let us go for material. I want to assign a material for my antenna. So I'll click the material editor. So I'll be getting a material editor box. Here I will be selecting material as metallic wire because I want to go with metallic element. And the wire properties, if you see in the design document, what we have seen earlier, the wire properties is 1 mm of radius. So I'm setting it to 1 mm. Yeah. So I'm setting it to 1 mm and I'll just click on apply. So I've got one of my material property ready. So I've used a metallic material for this particular antenna and I've created 1 mm radius metallic material. So once this is done, now next what you need to do is we have to go for medium. So medium, under medium, I have to create an exterior medium around my antenna. So here I have to specify my part number. So I have only one part which is specified, that you have to select it from your list, whatever you will be getting it. Once you click on that, click on OK. So your part list will be available under the exterior menu. So if you have n number of parts, all the parts should be available under the exterior menu. That is what is a recommendation what we have. It's a requirement what we have. We have to put all the things in the exterior boundary. So once you are done with this, click on apply. So we are done with the medium assignment. Similarly, frequency of operation. So frequency of operation, if I want to go about, I just want to sweep around like for 21 different frequencies. So if I want to go for 21 different frequencies, I have to select interval. I have to specify my start and end. So start is nothing but your 433.7. Here you have to write your megahertz in terms of e power 6. So you can specify E6. So here we'll be getting 433.7 megahertz. And end point is nothing but 453.7 e power 6. And number of frequencies, I want to start from 433, I want to end at 453. So if I put 21 points, including 433, I'll be getting 21 frequencies up to 453.7 with exact 100 megahertz of bandwidth. Like if you just click on 21 and click on add, you can see 433.7, 434.7, 435.7, 436.7, and so on. So with 100 megahertz of band, you're actually with 10 megahertz of band, you're actually trying to split it up. So these are the frequency regions what we have. So we can plot the parameters for all the different frequencies what we have. And then click on apply. So now the frequency assignment is also done. Later close the frequency part. Now go to CEM. So you're done with your medium, you're done with your frequency. And now we have to go with source. Let us select a source as delta gap because dipoles will work with the delta gap concept. And the excitation, whatever we want is 1 plus J0, that is what is already available, and characteristic impedance should be 50 ohms. It's available. Now we have to select the nodes. So it will actually ask us to pick the node. Either you can pick the node exactly in the middle or you can open the node list. So you'll be getting a node list, right? So once you've got the node list, select the node and try to see the preview. So this is not the point. So we have to go for the other node. So this is exactly at the center of your antenna. So dipole should be exactly feeded exactly at the center of your antenna. So once you're done with this selection, once you're done with this application, once you click on apply, so feed will be applied. Now you can actually check out whether the distance is properly available or not. You can go for tools, go for measure, select this point to this point. Okay, exactly in the middle. And even you can highlight your source also. Even you can highlight your source. The source is exactly at the same point. Okay, so this is how we have to actually set it up. So done, close it. So we have exactly excited exactly in the middle. And now once it is done, now we have to go for the outputs. Under outputs, I have to specify my far field sphere around my antenna in order to analyze the performance in the far field. So just click on far field sphere. So let it be the same with 1 degree step. Theta let it be 0 to 180 and phi let it be 0 to 360. elevation angle and azimuth angle, and then excite a power here within the far field. Try to get the power regions as well. Click on apply. So far field is also applied. This is fine. Now what I have to do is I have to go for single excitation. I have to select my delta gap. Click on assign, right click on the delta gap, click on assign, select the delta gap, whatever you have created so far, click on OK. Once it is done, now let us just go for fields. So right click on the far field sphere, select this, right click on the far field sphere, go to assign. You will be getting a far field sphere what you have created earlier. Just click on apply. So that will be connected. Then I want to analyze my surface power, surface currents, and even the far field results on the same excitation. So I'll click on apply. So this is nothing but your excitation menu. So if you see, this is your excitation menu. So this is what is your excitation. You are exciting with delta gap. You want to evaluate your far field sphere with this particular range, and you want to evaluate currents and surface power in the design. And even port modes also, if you want to analyze, you can just click on port modes and click on apply. So this is done. Now what we have to do is, let us go to part manager and apply a part. So whatever type of part you have taken, select your material what you have chosen, just attach the material to your particular antenna. So now your particular antenna will behave with this particular behavior. Okay, so now if you check in the part manager, you can see the dipole antenna is assigned with a material, metallic material. So once this is done, now what we have to do is we have to select output parameters. Let us go for output parameters. Final output, select final output. Select the delta source, because by default you have already selected the delta. You have got the delta source. If you are going with the port excitation, you will be getting this particular port excitations. If you are going with near field, you will be getting this kind of things. These are the scatter fields are defaultly available. And similarly, I want to analyze my currents also on the electric and magnetic field lines. So these lines are tick already. So I didn't do any other corrections. Already it was pre-builtly available. Okay, just click on OK. So this is done. Now under output parameters, you should be also assigning your length unit. Let it be mm. Instead of meters, let it be mm. Click on apply. So once you click on apply, your complete design will be available within a single screen. So once this is done, what we can do is, now you can go to solver, settings. So here you can see different type of solvers like MOM solver, multipole solver, FEM solver, MOM PO solver, MLFM PO solver, and PO solver. Whatever solver parameters I have specified earlier, this is how we'll be actually accessing the solvers. So here we have an option called as out of core block size. Also you can specify out of core in the sense it uses your internal memory of your CPU or else your HDD drive to compute the complete results. In order to produce a finite results within a less amount of time, it tries to compute that. So let us just go for MOM itself, plain MOM. Just let us just click on OK. I don't want to change any other things in this. Now you're done with all the parts. What you have to do is always, once you're done with the complete design, you have to go for save project. So once you click on save project, let us just create a new folder. Let us just create a new folder, that is dipole underscore antenna. So let us just save this. So I have saved it. The reason why exactly I've saved my project file is, if I save my project file, what exactly I'll be getting is, see, now I've saved two things. If I open my files now, so I have got dipole underscore antenna. I have got dipole antenna underscore dot DAT, dipole antenna underscore dipole antenna dot MTR, Antenna.vdb in the sense it's a visual database, what we can call, or virtual database, what we call. That is related to your antenna. Whatever antenna you have prepared, whatever parts are available in that antenna, and all the properties like frequency and the all other parameters will be available in this VDB file. And BEM is a mesh file. So we can actually analyze each and every file before getting started with a particular design. So once you save this project, then only in the job manager, so go to SEM, go to job manager. Once you save only, then only you'll be getting the execution path. Execution path will be defaultly available. Working directory will be available. Input file will be acquired when, if and only if you are saving your design into the folder. That is what is important. So this is one thing. So here we have got this particular thing. So it's fine. Now we can run the things. So, but before running, I would like to just show you some other things as well. So whatever dipole antenna files, whatever we have got so far, what are these files? What are these files are related to? All these things I just want to analyze. So first of all, I'll open a DAT file. Okay. So in DAT file, if you see, I'm able to give my input file, material file as an input. I'm giving what are the frequencies. So that file will be acquired. That file will be available whenever you have saved a project in a particular folder from your Visual SEM. So how many frequencies you want to run? Similarly, what is the delta gap you have given? What is the far field sphere value you have given? Similarly, what are the computations you want to do in the output module part? And what is a solver? What is the block size? So all these informations will be completely available in the .dat file. So material file, we are getting it from dipole antenna.mtr. In time convention, you will be getting input plus output. So frequency, you have 21. Time convention, I didn't do anything in time convention in my design. So I've put 21 frequency points. Excitations and sources, I've put delta gap, and then far field sphere for the excitation. For diagnostic section, I've used far field sphere as 0 to 180 with 1 degree shift, and 5 also 0 to 360 with 1 degree shift. And output module, whatever I have utilized, this particular output module will actually has a different parameters to be entered. So all the parameters, whatever are available from your design, will be saved into the memory, saved into .dat file. And this .bem file is nothing but .bem file is nothing but it is related to mesh. So if I want to open this, I can go with open with option. I can go to more apps. I can go to notepad. I can just click on OK. So now I can see what is the information on this particular BEM file. So on the BEM file, you can see we have got the information about the part 1. What is the part you have selected? How exactly you're bifurcating your parts. Yeah, how exactly you're bifurcating the parts, 10 parts, whatever you have given, how exactly you're bifurcating them. End wire, and then parts, how many parts you have. And end of the parts. So one part I have, then one part name itself is one dipole antenna. So we'll try to see the other files also, like BEM file and the MTR files also for all the antennas. Then we'll come to a conclusion how exactly it is working out. Okay, so now if I go for material, you can see there is the description of the material, whatever you are using. So material 1 type is wire, subtype is wire again with a 0.001. That is nothing but 1 mm. So it is representing the wire thickness in terms of 1 meter. So that has been treated as 0.001 millimeter. So we have got this particular thing along with the timestamp and each and everything, the data will be preserved. So once you're done with all these things, the dipole.vdb is nothing but your final design, what you have done and under your PC. So that is what is the thing. So once you're done with the complete results and the other things, then we have to go for visual viewer. So visual viewer is nothing but your result window, wherein you'll be actually getting the results. Okay, so in SEM, let us just cross verify. Material editor is already done. We have edited the material part already. We have assigned it. Job manager, it's running. It's for running your design. Let us run it. We have given the medium also, and then frequency we have given. Similarly, sources we have given, and then excitation we have given. Output parameters, far field outputs we have given far field sphere, output parameters, final output and length unit. So these are the parameters what we have done so far in the SEM window. So now let us just go for job manager. We've already saved the design. Let us just try to run it. So it took very less time for us to run. Since I went with the dipole antenna, it took very less time for me to complete the design part and the analysis part as well. So I'll just click on close. Now I'll switch the mode to viewer. So under viewer, let us just have a visualization on the 3D part. So in order to add up some solutions, we have to go for import and plot curve. So once we have got this import and plot curve, so here we can put the description where whichever data you want to acquire, but the file, the result file, whatever we'll be getting it, it's nothing but dipole underscore antenna dot erfh5. So erfh5 stands for your result file. So whenever you see dot erfh5 in the antenna designing, especially when you're dealing with frequency domain, you can actually select that particular erfh5 file to see the results. So I'll just click on apply and open. So here we have contour and we have curve. Under contour, we have node and spherical grid. If I select spherical grid, I can go ahead with far field, the different reports. So you can see n number of frequencies we have, only one excitation will be available. So we can go ahead with the 2D results as well. Let us just get started with the 3D result first. So let us just select this contour. So we have got the contour part. So let us just select this electrical wire current and place your antenna exactly in the middle. You can see the excitation is exactly in the middle. So it is spreading in the equivalent wavelengths, equivalent power of things. So this is for your electrical wire current. So if you want to see one after the other, how exactly those are responding. Now let us go for spherical grid. Let us select far field. So let us go for field. Let us select the gain, whatever we have got so far. Close. So we can visualize the different patterns because the antenna was completely radiating it, the different frequency. So if you select this frequency, desirable frequency, then the performance of the antenna will actually change. So this is how we'll be actually going ahead. So if you just click on this, you can see the excitation patterns of all the 21 frequencies, whatever you've allocated for. So this is how actually you'll be getting the patterns out there. And this is how we'll be actually getting the electrical wire currents. So once this is done, you can also go ahead with 2D result visualizations also. So let us go for file. Let us go for import and plot curves. Let us just select this contour, go for spherical grid. Let us just try to evaluate the result. For 443.7 megahertz. Let it be at a fixed phi of 0 degrees. Let it be plotted. So this is nothing but your beam coverage. Yeah, this is nothing but your beam coverage, whatever we are getting it. So field, we have to specify the field here. Click on OK. So this is how we are actually getting the pattern out there. So this is how actually we'll be running the complete design flow, how to go about and how to get started with all those things. So initially we started with mesh, and even the complete documentation is available for each and every step, whatever we have done so far. Like you can see all the steps, like starting from the node point, whatever we have done, the curve, sketch curve, and then curve with a generate 1D of either. You can go with this methodology also. So the frequencies, whatever frequencies we want to work with, and then we have allocated the delta gap source. This is available. Along with that, we have got a node window, so we have to allocate the node window. And then this is a far field sphere. What we have, so far field sphere, we are applying with 1 degree of phase. We have done with that. So I have allocated all the required results, whatever we want to project, and then delta gap has been selected. Far field has been selected, and then you can see currents have been selected. So we have to select this kind of parameters. This is already done, and then we have changed the units to we have clicked on save projects, went to job manager. We have got the same kind of menu, and then we have clicked on run. So once we click on run, it took few seconds to run it up, and then it was done. So we went to viewer. Under viewer, we have got the different type of results. So input impedance and reflection coefficient, all the other stuff, which we can plot it up. Similarly, wire currents also, if you want to plot it, you can do that. Electrical wire current, we have gone through electrical wire current. We've got this. Similarly, the gain, what we have specified here. So these are the lobe directions, what are already been specified. So we can also specify in that particular fashion. So this is a complete procedure, how exactly we have to go about. So we have to follow this particular methodology to go about and finish the things. So this is a detailed flow, how exactly we have to go about with a single antenna. So is this antenna is clear to everyone, or else do you have any doubts in this particular thing? If there are any doubts, please just post it in the chat box. If time permits now, we'll just try to have a quick answers on this particular thing. So if we follow the same steps, whatever this particular document prefers, we can go ahead with a particular implementation. We can clearly understand it. So in the same way, students can also take a different frequency, can calculate the theoretical values and can put the approximate value for a theoretical and can design the things actually. So are there any doubts to discuss on that this particular antenna? So if we go to this particular results visualization, we can go ahead with all the different type of plottings and etc. So I just left out with this particular thing, which I would like to show it to you.
Rohit sir,
Yes, sir.
can you give time to the student? Is it,
Yeah, sure, sir. Sure, sir.
5 minutes they can break and then they can check once the steps.
Yeah,
Right?
sure, 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 sir. Sure, sir.
Just check one of the student if either they are going to design first this or we should start another design first. Then last 1 hour they can practice.
Yeah, let us go for last 1 hour practice, sir. So let them take some break. I'll
Okay.
show them one more design. So in that we have other steps and other mode of excitation. So they'll have a observation for both of those, and then they can go ahead for implementation.
Fine, sir. So this link, na, this PDF you can share so some student they can go through
Yes,
now.
sir. 1 second.
Yeah.
Sir, should I share it to you with the mail, sir, or else is there any possibility to drop down all the things in this? Because
In the message you can't keep.
the PDF file, sir, is it possible?
Yeah, you can drop the.
1 second, 1 second. I'll try it, sir. Because I'm in guest privilege, I am not sure whether I have that opportunity or not. Let me just check it out. So already whatever introduction I've given earlier also, I'll be putting that also, sir. No, it's not allowing.
Other you can send me in the my mail, sir, if you have.
Yeah,
I will try to drop in this.
yeah. I'll do that, sir. I'll do that.
And just to check once message, what are the few questions if there, then
Yes, sir. Yes, sir. Just let me know, sir.
can-
Yeah, yeah, yeah.
if people are not there also, at least recorded they will get.
Yes, sir. Yes, sir.
But they should not leave this one, what is called meeting.
Yes, sir. Yes, sir.
I think 420 we can have another design.
Yes, sir. Yes, sir. So we'll resume back at 420. Is it, sir?
Yeah, I think 16:11. So I think 4:12 now. Only 8
Yes.
minutes we can.
Yeah, yeah. Fine, sir. Fine, sir. No issue. And in the meanwhile, I'll be sharing you the documents.
Yes, yes. to PDF share in the team. Okay, you can check in the team also. I think channel, check the resource material.
Sir, can we start, sir, or else we'll wait, sir?
No, sir, we will start.
Okay, fine, fine, sir.
Sir, your mic is muted.
Rohit, you are muted actually.
Yeah, sorry for that, sir. Yeah, so here what exactly we are doing is we have got the resources from ESI. Once you install the Visual Sim software, you have got the resources actually in under C drive wherever you have installed it. So we'll be getting a program files. Under that you have ESI group, you have SEM1 2021.0, whatever version you have installed, and then you have examples folder. On this examples folder, we'll be actually having this SEM-FD, SEM-HF. So different type of examples are readily available. So you can pick up the examples from this in order to understand the concept and how exactly you have to assign the excitations. All the parameters you can completely analyze. So as of now, I took horn.igs file from this particular file. Okay, horn_ve example. I have took horn.igs. So you can directly open up the design under mesh window. So initially, whenever you drop your design IGS file, you'll be getting it in this particular format, in the wireframe format. So if you want to edit this particular format, what you can do is you can go for flat wireframe format in order to get this. So here now you can see how to rotate and how to pan and how to zoom in, zoom out. So if I click and hold my mouse scroll button, and if I want to rotate it, I can rotate it as per my requirement. Okay, so I can just click, hold on my mouse cursor and I can rotate it. Similarly, once you want to realign it, you have to just click on this center button of this axis. So once you click on center button of the axis, however your antenna has been positioned, you'll be actually getting that particular positioning. So this is done. Now we have to allocate the parts for each and everything. If you want to pan, pan your complete on, front, back, forward, etc. You can scroll it. You can pan it across. You have to right click, press a right click on the structure, hold it, and try to move it. That's it. And similarly, zoom in, zoom out to maximize and minimize your design. So in this design, what you have to do is, here at the top, you have a selection window. This is nothing but your selection window. How exactly you want to select it, you have to go about. And here you can see by default, whenever you're dropping down IGS file from any other softwares or any other CAD tools, you will be getting default one part only. You have to now split up the parts as per the requirement. So now what I'll try to do is, in order to split up the parts, we have a selection entities here. Basic entity in the sense it selects up the complete antenna. If I go for surface, I can select surface by surface. Okay, now I have selected surface. The mode is surface by surface selection. So once this is done, now I have to select my surfaces. So just click on regions, that's it. So outer regions, all the outer regions, I'm selecting it. So all the outer regions, select it carefully. So once we are done with this, yeah, so we are done with almost all outer regions. So outer regions are almost like 24. At the bottom side of your screen, you can see how many surfaces you have actually selected for. Okay, which will give you the count. So once this is done, now I want to generate a new part out of old part. So you have to right click after selection, you have to right click, go to tools, under tools, you have to select add to new part. So once you click on add to new part, this particular surface will be added to a new part and will be named as part 2. So once you're done with this part 2, in order to go with easier implementation, one benefit in Visual Sim is you can also make it invisible also. So you can just click on this particular globe symbol, particular point symbol. So if you make it empty, what happens is you can see the complete outer surface is completely removed. Yeah, you can make it hide or you can make it invisible. So apart from this, now I want to select the inner region. So in order to select the inner region, again, let it be surface by surface only. Now select all the parts. So we have selected all the parts. We have selected all the parts for the inner surface especially. So just right click on this, go to tools, right click, go to tools, add to new part. So this will be selected as an inner part now. Now the last selection, what you need to do is you have to select for the port. So there is only one surface for the port. Select it, right click, go to tools, go to add to new part. So we are done with this particular thing. So we have got all the three parts. Now you can see the level 1, whatever, see it is empty. So if you click on F11, that is part manager, you will be actually getting what kind of parts you have. Okay. So part manager. So level 1 is completely empty. It doesn't contain any surfaces because I've already extracted all the surfaces from level 1. So I have to rename all the parts, whatever I've got it. So metallic surface. And then this is nothing but probe, I'll call it. And this is nothing but my port. Okay, I'm done with this particular thing. So this particular horn antenna, if you go with the design documentation of this particular horn antenna, this horn antenna is actually working at, it works at 8.2 to 12.4 gigahertz. It's exclusively working in the X-band frequency. So we have to calculate the lambda by 7 or lambda by 3 would be the optimal size. So we'll try to calculate the lambda. Here, my operation range of frequency, what I want to put for this antenna, I would like to go for 10 gigahertz. Okay. So we are done with all these things. Now, since it's an empty part, right click on that, go to delete, click on delete. So it gets deleted up. So now you're done with your complete horn part. So this is absolutely fine. Now what you have to do is go to 2D. Under 2D, we have an option called as Topo Mesh. So under Topo Mesh, it actually gives me the element size. So now here, what I can do is I can specify my Topo Mesh as 6. How exactly you have to specify 6 is basically, let us again go for calculation. Three into 10 to the power of 8 divided by, it's 10 gigahertz, right? 10 gigahertz. So 10 into, so here I'm getting almost like close to 30 mm. I'm getting it. It's 0.03 meters. That is nothing but in 2000. If you do 30 mm, I'm getting it. So here I have to check with the mm size. So I can either go for lambda by 5. This is a representation what everyone has to remember. So basically, whenever you're trying to create some mesh elements are usually based on the lambda size. So you have to either go for lambda by 5 or lambda by 7, lambda by 11 based on the resolution what you want to get with. So since this is an X-band antenna, you can go for lambda by 5. So lambda by 5 in the sense 30 mm divided by 5, if you go ahead, you will be getting somewhere like 6 mm. So you can select each and every mesh size of 6 mm. That's how it has been calculated. So here we are getting in terms of meters, 0.030 meters in the sense 30 mm. 1 meter is equal to 1000 mm. So 30 mm. 30 mm you are converting into lambda by 5. So lambda is 30. Lambda by 5 is nothing but 6 mm. You are giving 6 mm here. So this is fine. Now what we have to do is you have to go for edge group. Already I have given 6 mm as a size. Whenever you are solving this kind of problems, like if you are going with horn antenna, or else if you're going with any antennas which are actually feeding with a port. So what you have to do is, usually the port should have the higher mesh, should have the higher number of elements when compared to the complete antenna. So here also we'll try to do the same thing. Just click on plus symbol. So here you'll be getting edge group. Select the edges, whatever edges you have, right? Select all the edges. Select all the edges, click on modify. Here change the value to exactly half of the original mesh size, whatever you have put. Original mesh size you have put it as 6. Half of the mesh size will be 3. Let us go for that. Once you are done with all these meshing operations, click on mesh all surfaces. So once you click on mesh all surfaces, you can see the proper meshing would be done on all the surfaces. So these are the elements or unknowns which will be actually evaluated by your tool. So each and every triangle will be evaluated by your tool with the proper integration techniques and electromagnetic equations will be pushed down into a matrix. Thereby the RHS computations will be done. So this is how it will be solved up. So now you can also check the element normal. So you're done with the mesh. So here you can see the number of elements. So you're getting somewhere like 2070 elements. Now we have to solve all 2070 elements to completely provide the results. So this is one methodology. So now let us go for checking the element normals. So just click on check, go to element normals, just click on check. So here you want to represent the color normals by arrows. Just click on arrows. So once you click on arrows, you will be in a position to observe the complete arrows. So if you see, the complete antenna arrows are towards inside. So this is a proper thing. In horn antennas, whenever you're going, this particular orientation should be available. And moreover, if you see the port, the lines, the element lines should be inside the port. If I remove this port, if you see, this should be inside the port. Wait, I'll just show you. See, now if you see my field lines are completely inside. That means whatever I'm trying to feed it to my antenna, that is properly entering into my antenna. That is what is a perception, what we should have. So whenever you are trying to create some port based antennas, this is one of the basic tip everyone has to remember. Earlier in the dipole antenna design, we didn't go with any port excitations. That's the reason we didn't go with any checks. So here, after doing checks, basically you'll be getting an option saying that orientation of 2D mesh normals is uniform. So if you are getting this particular message, that means your design is proper. There is no sort of issue with your design. In terms of syntactical approach, there is no sort of issue. So this is one assurance what we'll be getting it. Okay. So once we are done with this, click on apply, close. All modifications are accepted. Orientations of 2D mesh normals is uniform. So this is absolutely fine. Now we can go ahead with our SEM window. Okay, just click on the SEM window. So you can also cross verify how exactly it goes about. So meshing operation. So here we went with Topo Mesh 6 mm, given the edge also like 8.3. So we have selected all these edges. We have refined the mesh. And then now we have to go for the parameters, all the parameters. So this is for SEM window. Until this part, whatever we have done, it's absolutely the same. So let us just go ahead with that. So now I want to assign under SEM window, I will just check with the view once again. Yeah, I have E field FD, it is absolutely fine. Now if I go to SEM window, first operation what I have to do is medium. I have to assign an exterior medium around it. Then only I can do some port excitations. Otherwise, if I'm not including my port in the exterior medium, the port will be outside the box. So it will not allow me to create it. So go to part, select this, click on the parts, select all the parts, whatever are available, click on OK. So 2, 3, 4 parts are added up, click on apply. So all these parts are added into an exterior boundary which has been created. So once you are done with this particular thing, then what we can do is go for boundary conditions. I want to create a PEC boundary around my particular metallic surface. So go to boundary condition, PEC, select PEC, click on apply, close it. So one PEC will be available under the boundary box. Next, go to frequency. Here I want to operate single frequency only. Let me just go for frequency. Let me cross verify once again. Yeah, it's 10 gigahertz. So 10 E9 I have to enter into this particular thing. 10 E9. So 10 E9, click on add and then click on apply. Then only your frequency is applied. Okay. Always remember, enter your frequency values, click on add and then click on apply. So this is done. So this is already done. Now frequency part is already done. Now we can go with port. So select port, click here. So automatically whatever port you have created with the rectangular box, that will be highlighted. So this is one good feature. So whichever ports you have selected in your design, automatically those ports will be selected. Select your port, go to OK and go to mode solver. In mode solver, since you're going with the rectangular mode solving here, go with analytical rectangular and then modes will be TE10 mode. By default, if you want to excite your one second, I'll just try to rearrange this. Yeah. If you want to excite your port, your waveguide port, what you need to do is you have to go for TE10 mode. So once you're done with these all things, you have to click on apply. So in this stage, if you are getting any sort of errors, that means you didn't assign any medium. So always remember, always you have to start with a medium. You have to assign an exterior medium around your particular antenna, all the parts of the antenna. And then boundary condition we have assigned it, frequency we are done with, port we have excited, it's properly fine. Now I have to go for my outputs. I have to give my far field sphere. Let it be the same 1 degree step size. I want to use it. Far field power, let it be on. Click on apply. So we are done with this particular part. Close it. Go to SEM. Under SEM, again you have single excitation. Go for single excitation. Wait a second. So for this, especially when you're dealing with ports, what happens is you don't need to go to single excitation. Automatically, how many ports you are creating, the excitation will be automatically created. We don't need to create anything else. So here you can see single excitation. If you double click on the excitation box, you'll be getting excitation box. So here mode is already been assigned. Now select your far field sphere, assign whatever sphere you have already created, select it, click on OK, done with this. Now select your currents, surface power, port modes. If you want to select, go ahead with that and click on apply. So once we are done with this, excitation is also applied. Now what I can do is I can go with this. Now I can go with my output parameters. I have to give my final output. So final output. So here you can go for S matrix. Similarly, I just want to go ahead with far field. So I have to calculate this far fields also. So I'm specifying the far fields. So input power, scattering matrix, admittance matrix. Apart from that, far fields, the complete far field results I want to visualize. So I'm selecting all those things, click on then OK. So once you are done with that particular part, you are done with your output configuration. So next step, go to output parameters, go to your length unit, set it to mm. If it is an mm, absolutely fine. So once you are done with all these things, next step what you have to do is, now we have to assign the materials. So there is one material which is pending, which I have to assign for my probe. So there is a material which is called as probes. You can select probe here. So under probe, go to general, click on apply. So generic probe, we are trying to use it here. So we are done with all the things. So now I have to assign my materials, whatever materials I want to use with my antenna, I have to do that. So go to part manager. In part manager, the metallic object, the metallic out surface of the horn antenna will be assigned with a PEC. Done. And then probe will be assigned with a generic material, generic probe, whatever you have created. Port automatically will select PRT1, whatever port you have created, automatically it gets assigned to that. So click on close. Now it's saved. Now we have the complete information of all the parts. So everything is done. You can cross verify the steps as well here also. So this is a typical flow. First we'll start up with the medium, then we'll give the boundary condition if and only if it is required. Then we'll go ahead with the frequency of operation. Then we'll go ahead with port excitation. Then we'll be going ahead with after port. We'll be going ahead with far field sphere, the output, and then generic probe I have applied. So materials are already been assigned. And in the source, I have got it. This, since is an older resource, we've got it in this way. Basically, we'll be getting in the excitation format. Excitation mode, you will be getting it. And there you have assigned. You have to assign your far field sphere, near fields, currents, surface power, port modes, etc. So once it is done, select your far field sphere, assign it, and select all your parameters, whatever you want to visualize. And then length unit, set it to mm. Click on save project. So running the solvers, this is the last step what you need to do. So if I approximately compute the size of this particular antenna, it's somewhere like almost 285 mm. So it's almost equivalent to your 10 lambda. So here for this case also we can go ahead with MOM logic. If your antenna is further more complex, like greater than 10 lambda to 100 lambda, then you have to go ahead with MLFMM logic. So this is just an approximate distance measurement what I've done here. So it's a diagonal distance what I've calculated. It would be furthermore less only. So once it is done, now the solver settings by default will be available with MOM. Okay, so all the parameters are properly done. Now what you can do is go for save project. So while saving the project, you have to select a folder where you want to save your complete results, and you can save there. Save it. So once you have saved your project, also save your VDB file also. So next time when you're opening your project directly, you can continue from this stage. You'll have all the properties saved. Everything will be readily available. You can directly run the design and then you can evaluate the results. So in this, now let us go for SEM. Let us go for job manager. So now in job manager, you can see input file is also readily available. So once you start saving it, then only your input file .dat will be available. So just click on run. So it takes few seconds to run this particular horn antenna design. So one good thing in ESI SEM1 software, what I observe is basically it shows you the detailed procedure, what exactly happens in the backend also. So wherein the customer or the participant can also view what is the status is going on, what is the stage it is going on with, what are the different stages it has. All those things we can analyze. See, it almost took somewhere like 27 seconds. Okay, so the stages, if you analyze, so processing your far field responses, factorizing your block rows. So first thing is factorizing the block rows will be there, and it has took number of triangles whatever we have assigned for the medium. And then you can see assembling the port size is 2160 cross 144. Factorizing, assembling, factorizing, solving the problem in terms of far field, and then exporting the results. So this is what is a procedure has been done with this particular technique. So once it is done, you can click on any key to close it. So you are done with this, close it, click on close. Now let us just go for viewer window. So in viewer window, go to file, go to import and plot curves. Select this particular folder. Go to desktop or wherever you have saved the file, go to that particular location. Select your antenna and select your ERFH5 file, what you have generated, the result file, whatever you have generated. Then click on open. So we have got the result file in this particular format. So you can go for contour, you can go for spherical grid, you can go for the excitation, field versus angle, you can go ahead with. Field, now you can assign your gain parameter here. So once you are done with the gain parameter, you can go ahead with the plotting. So this is not a proper angle of plotting it. Okay, so this is how your actual antenna pattern will plot it up. So you have to calculate at fixed phi is equal to 0 degrees. So this is how you are getting it. So now let us also analyze the 3D result as well. So let me just change this to new window page. So let us go for polar. Let us go for the same sort of results. See, this is how your horn antenna pattern will come. Okay, so this is how your gain will be propagated. Now let us just see the response, how exactly your antenna is working up. Okay, just close this. Close this. Click on this particular page. Click on this particular page icon, this part, and then go to your results. Go to contour. Under contour, you have node. Go to electrical field mode. So you can see the excitation on the particular port lines. The electrical surface current, how exactly the surface currents are feeding through the probe and the other stuff. Similarly, spherical grid, far field. So this one we have to set it up. Go to field, go to factors, assign your part. And instead of linear, if you're going with 10 dB, you will be getting a different pattern out there. Okay. So this is how your horn antenna pattern will look like. So if you go for 20 dB scale, you can see the result. Okay, exactly at the port, you are getting this kind of result. So basically these horn antennas, whatever horn antennas will be designing it, these horn antennas are nothing but those are directional in nature and also are helpful in providing higher gain values. So if you see some properties of horn antennas, so a horn antenna, it's also called as a microwave horn antenna. Basically, for high frequencies also we can run the horn antenna. But this particular antenna is a directional antenna. Directional antenna in the sense, in the result, if you observe, the antenna gain is towards forward direction. That means wherever the flaring end is there, at that particular end, you can actually see the exact results, exact pattern, which is pointing towards that particular direction. You can see there is a higher lobe, right, which is onto this particular direction. So in this particular direction, your horn antenna will start radiating. So that is what is one thing what we need to understand. Okay, almost in 20 dB gain, if I put almost I'm getting 36.990 dB. Okay, 20 dBi gain I've put it. So linear, if you put it linear, you'll be just getting a pattern out there. So that's where you can visualize actually. You can go to contour, go to field, you can adjust the scales actually. 10 dB if you put it, 18 dB. Generally, basically, we'll be observing the results in terms of 10 dB scales. So in 10 dB scales, if you go ahead, we are getting somewhere like 18.49 dB. Similarly, in linear scale, if you're going with somewhere like 70.72, we are getting it. So you can see here also the direction is towards forward. Okay. So how exactly this horn antennas will be getting started up? I mean, how exactly these things are working? So basically, if you see, horn antennas are microwave antennas which are completely made up of the waveguide filters, waveguide structures. So we have a structure which is called as a waveguide. So we'll be actually flaring one end of the waveguide in order to provide the higher beam and higher gain. So we can set up a horn antenna which actually runs for higher frequency ranges with a higher gain as well. So these are different type of horn antennas what we have. So if you have a look at waveguide, how exactly waveguide looks like. Let's go for rectangular waveguide. So this is nothing but your rectangular waveguide. Yeah, so this is nothing but your rectangular waveguide. So we'll be actually taking the waveguide only. One end of your waveguide will be feeded. One end of your waveguide will be flared actually, flared with a specific angle and a specific dimensions. So even though if you see this particular antenna design, you'll be actually having some parameters.
Rohit sir.
Yes, sir.
Is it a screen changed? Your horn.